In this video, I'm going to talk about relation between the phase values and line values in a delta connection. Okay, it could be a load or a generator, it doesn't matter. Okay, as I said, if it is a load, current is going to go in. If it is a generator, current is going to go out. Okay, so similar to the star, please look into my previous video before coming to this video. So here the three windings, we are connecting them in delta. So here is A prime, B, this is B prime, C and C prime. So A prime, B connected together, B prime and C connected together, C prime and A connected together. Okay, so here there is no neutral, only three wires coming out from here. So wire is coming out from here is called line A, line B and line C. Okay, so as I mentioned, this is called line, this is called phase. Okay, now what is the phase voltage? Voltage between A and A prime. So this is A prime. Now what is the voltage between AB? Between here, between two lines, VAB. So can I here call VAA prime is same as VAB? So this is phase voltage, this is line voltage. So basically what I'm saying, in delta, when it comes to delta connection, the phase current equal to line current. In delta, phase current equal to line, in delta, phase voltage equal to line voltage, my apology. So when it comes to delta, phase voltage equal to line voltage. Now when it comes to the current, let me erase this part. Okay, so when it comes to the current, so basically this is the phase current, the current passing through the phase, that's a line current. Okay, so the phase current is coming towards A. At the same time, when you look at VCA, current is going out, right? That's IPH, that's the phase current going out. So the IPH is coming in right there, but there is a phase angle between these three. Okay, between these two, IPH A, this is IPH C. Okay, now if you look at these, apply KCL, Kirchhoff's current law. IL is going out, one IPHC is going out of the junction, IPHA is coming into the junction. So IPHA equal to I line plus IPHC, because these two currents are going out of the junction, A is coming into the junction. That's KCL, Kirchhoff's current law. So if you apply this, so basically my line current is nothing but IPHA minus IPHC equal to I line. So same principle, look into the previous video. If you use the same principle, where is it? See here, VAN is 120 at an angle of 0, VBN is minus 120 at an angle of minus 120. VAB is nothing but VAN minus VBN. So there are the voltages, but when it comes to the current, same principle we can use, IPHA minus IPHC. So say IPHA is say 30 at an angle of 0, IPHC, since I'm assuming it's a symmetrical load. So when it comes to the load, there are two types. One is symmetrical, another one is asymmetrical. Symmetrical means whatever we connect here, the load, each phase will have the same value. That's called symmetrical load. Asymmetrical means each phase will have different amount of load. Okay, usually we don't see asymmetrical load, most probably symmetrical loads. So in this class, I'm going to talk about only symmetrical loads. So if VPHA is 30 at an angle of 0, IPHC must be 30 at an angle of, this is C, right? So minus 240. So when we combine these two, you will end up with a relation between IPH and IL. The line current is always equal to √3 times phase current. line current is always higher than the phase current in delta. Okay, and power value is same both in star and delta. So when you draw a vector diagram in delta, we always draw them for phase values, currents, phase currents. When you draw a vector diagram in star, it's always phase voltage. When it comes to delta, it's always phase current. So IAB and IBC is 120 degrees apart, ICA is 120 degrees apart. Now, to get IA, we will draw negative ICA. Okay, now sum of IAB minus ICA, that's what IPHA, PHC. You're subtracting those two. When you subtract those two, you will end up with I line current, which is I'm indicating IA, okay, which is 30 degrees lagging. So when it comes to delta, the line current is 30 degrees lagging the phase current. Okay, so that's another important point. So far when you compare delta and star, okay, I want you to understand when we compare these two, star and delta. In star, VL equal to root 3 VPH. Here delta, VL equal to VPH. In star, IL equal to IPH. Here IL equal to square root 3 IPH. And power equal to 3 VPH IPH cos theta, or square root 3 VL IL cos theta. Power formulas are same both for star or delta, VPH IPH cos theta or square root 3 times VL IL cos theta. Another important point in star is VL line voltage leads phase voltage by 30 degrees. Okay, line value leads the phase value by 30 degrees. Here VL and VPH same. When it comes to delta, I line lags IPH by 30 degrees. Line current lags the phase current by 30 degrees. So you must remember this table, especially you must remember this table all the time when you're solving examples in this chapter. Okay, so all the examples are based on this. Now we'll solve a couple of examples here itself. So here is an example. I'm going to show you a simple example. Say it's a Y connected. Okay, it's a Y connected. I gave you, say for example, VAN equal to 120 at an angle of 30 degrees. Can you guys find VCA equal to how much? That's the question. Okay, so I gave you a star connected VAN equal to 120 at an angle of 0. I want you to find VCA. Okay, now we know VAN. Can you tell me what is VBN? If you know VAN, VBN must be 120 at an angle of 30 minus 120, so minus 90. VCN equal to 120 at an angle of 30 minus 240. Okay, so 120 at an angle of minus 210. Okay, so VCN equal to 120 at an angle of minus 210. Remember, sometimes you can say instead of minus 240 you can use plus 120, because all the three phases, so VA, VB, VC. Here I'm following this direction, saying that minus 240 degrees, or you can say plus 120 degrees. So you can say VCN equal to VCA plus 120. So, but I always follow the negative to be consistent with other examples. Now I know VCN, which is 120 at an angle of minus 210. So can I say my VCA? Okay, my goal is finding VCA. VCA is nothing but square root 3 times 120 at an angle of minus 210 plus 30 degrees. Why plus 30? Because VL leads VPH by 30 degrees. So basically, if you look at VCN is 120 at an angle of minus 210. So that's 0 degrees angle. Okay, minus 210 is nothing but this is minus 180 minus 210 is going to be somewhere here. That's VCN. Okay, VCA must be 30 degrees before this, right? Okay, so my apology, it's going to be before that is right there. Why is that? Because you're standing here rotating the vectors. So this is VCA. VCA is supposed to come 30 degrees before VCA. Sorry, VCA come 30 degrees before VCN. Okay, line current, line voltage supposed to come 30 degrees before phase voltage. I'm sorry, my energy levels are going down and probably I'm recording in the middle of the night, so that's the reason instead of current I'm saying voltage, or phase instead of phase I'm saying line. By the way, I'll end this video in a second and stop recording for today. So here, so VCA must come 30 degrees before VCN. So square root 3 times 120 at an angle of minus 210 plus 30. So what is VCA? Is nothing but square root 3 times 120. I believe this is 208 at an angle of minus 180 degrees. Okay, this is VCA. That's the answer. So next video, probably I'm going to record them tomorrow. In those videos I will solve at least few more examples based on this. Thank you.